Thank you very much, and hello everyone. My name is Hongyi, and I'm a PhD student supervised by Jan and Helena. I'm very happy to be here to have a chance to present my work, which is the federated learning and also the reinforced learning. So here, the topic I was going to present today is the coordinated and decentralized reinforced learning architecture with adaptive exploration and vector-based action selection. So here's the outline what I'm going to present today. First, I would like to give you the basic concept of the reinforced learning, and then I would like to present the result at the Chalmers and also our collaboration with software center companies. And then I'm going to give you the conclusion and also the future research direction. So here first is the basic concept of reinforced learning. The basic concept is very straightforward. So in the reinforced learning, we have an agent who will interact with the environment, and that environment will provide you the numeric reward signals. And the task of the agent is to find the optimal policy which can map the state to the actions, which will automatically result in the maximize the long-term measurements of the reward. So here we have the basic algorithm, which is the Q-learning. This is the Q-table-based action selection, but we have a superior algorithm, which is based on the Q-learning. We have the deep Q network, where we use the neural network to replace the Q-table and to present the Q-table generation. So here is the concept of the deep Q network. The DQN is better than the Q-learning. We have the three strategies here. The first is neural network. We replace the Q-table to calculate the Q-value in order to solve the issue of dimension explosion. The second is the experience replay with the random batch selection to remove the relevance between different kind of the data samples. And then we have to fix the Q target for the better network convergence. So in this sprint, what we have done is we proposed a decentralized reinforced learning architecture combined with the federated aggregation idea, so we can have the opportunity to remove the central interaction in the whole system. So on the figure on the right hand side, you can see there's the very simple diagram for our system. So there are two different data exchange channels. With the green channel, we were going to share our model. So the model will be shared with the neighbors. And then with the local aggregation, each of the agents will gain the knowledge with the neighbors to also improve the quality of their own models. And with the brown line is the sensor data exchange, where we were going to exchange the important information between each of the neighbors, such as the local metrics and also the local position and etc. So we collaborate with Ericsson to validate our algorithm. So the scenario is we deploy single or multiple UAV base station to integrate it in the public network using the IAB technology to fill the coverage hole for the mission critical users in the middle. So my objective is to design a machine learning algorithm to jointly optimize the antenna and also the UAV base station movement strategy to provide the best serve on-ground users while maintain a very good service quality. So here I show how we map our scenario state space to and also the action coding. So we have three different action options. Well, if we choose the 0 digits, that it means left jump, which means that the agent will moving backwards from the current step. If we select 1, and then the agent will hold and maintain at the same the status. And if we choose the 2, the digit 2, then it means right jump. We are going to moving forward from the current steps. And for each of the UAV, we have two two-dimensional state space, which is the x and y axis. Each of the axes will have 8 state options. And also, since we have 2 dimensions here, and in each of the dimensions we have 3 different action options. So in total we have 9 actions in the action code pool. When the agent will going to perform the action decision, it needs to choose one of the action from the action pool. So also how we design our reward function. So for us, we have selected 6 critical features in our scenario, which is the 5 percentile and 50 percentile throughput, both in the downlink and uplink, and also the uplink and downlink drop rate. So we used a weighted sum to represent our requirements, and also we assign different ratio for each of the our critical features. In our study, we choose 0.5 for our drop rate, we choose 0.3 for the 5 percentile throughput, and we choose 0.2 for our 50 percentile throughput. The reason why we choose these digits because we want to first prioritize the drop rate because we want all of the users get connected with the agent so they can all get the wireless connection. 0.3, 30% for the 5 percentile is because we want almost everyone get the connection and get a quite okay connection to the UAV base station. Then the rest, the 20% is for the 50 percentile throughput is we want to make sure that the average throughput is also be considered in our scenario. So here's our scenario diagram. So we showed what kind of local data has been shared in these 3 different UAV base stations. So the local data at the UAV base station is the 2-dimensional location of the UAV base station, and also the performance metrics of the served mission critical users, which including the 5 and 50 percentile throughput, including downlink and uplink, and also the drop rate. If considering the data exchange between each of the neighbors, we have the 2-dimensional locations and also the reward values, which is derived and calculated by each of the UAV base station. And here, in order to tackle the challenges, because we want to deploy those kind of UAV base station in our real-world environment, so we have proposed 2 strategies to cope with the real challenges when we are trying to make it simulate and also deploy it to the real environment. The first strategy we propose is adaptive exploration to cope with the environmental changes. For example, like the user movement. So here we monitor the reward value changes. So we trigger once we find out there's a reward value change and the drop is very large, we will trigger the update of the exploration probability. Then the agent will start to explore the new environment. The second is the value-based action selection. So this strategy is to use to improve the convergence speed and also the performance of the algorithm, because when we are deployed to a mission critical environment, we want the reinforcement learning algorithms to explore much faster. Then we can deliver a very quick service to our users. Yes. So yeah, here is the first the algorithm, the adaptive algorithms. As I said, here we are going to monitor the reward value drop. So we have a predefined reward value drop threshold. Once the reward has been dropped larger than our threshold, the exploration probability will be triggered and increased to 0.1. Then the agent will start to slowly explore the new environment. The second is the vector-based action selection. So here is the algorithm where we consider each of the action as the vector. So we introduce the direction in each of the action selection. And also we will evaluate the consequence of the previous action selection. If the previous selection will lead to the reward increase, then we will select in the future selection we will select the same direction if we compare with the previous action. And if it is not, we will consider that the previous action selection will lead to a very bad consequence. Then we will choose the opposite direction if we compare with the previous action selection. So here I would like to present the result. Here we have 4 different phases. The first phase is the training phase, where we pre-train the reinforcement learning using the older data set. And then we have phase 2, phase 3, and phase 4 is the deployment phase, where we deploy this UAV base station into the environment. And in each of the phase, we have introduced the user movement, so which means that the user distribution will be changed, and also all of the features and also all of the metrics will also be changed. So we use this strategy to evaluate our algorithm. So with the red line is our proposed multi-reinforcement learning algorithm. So we can see that it outperforms other baseline algorithms in terms of the convergence speed and also the convergent reward value in our scenario when dealing with different user distribution. The orange line is the retraining algorithm, which when we enter in the new phase, the reinforcement learning algorithm will clean all of the previous knowledge and retrain the network from scratch. So we can see that it needs more iterations to convergence if we compare with our proposed algorithm. And also the reusing model in the previous user distribution is really hard to convergence because it will reuse the previous knowledge, but it will not do any changes, even though the user distribution has been changed and all of the environment has been changed. Here is the numeric table result. So our observation is quite similar with the previous figure. So our proposed algorithm, it outperforms the baseline algorithm in our invalidation case and can reach about 86% of the optimal reward value. And also the performance of the machine learning algorithm is rely on the reward function design, which may depend on our requirements. So here is the bar figure I would like to present. So this is the performance comparison between if we deploy the UAV base station or we don't deploy the UAV base station if the central macro base station is destroyed. Our observation is if we compare with the no UAV base station case, after we deploy the UAV base station, it will significantly improve the system performance of the mission critical users, both in the throughput and also the drop rate. So I would like to give you my conclusion in a sprint. So we have the general conclusions. The UAV base stations with our algorithm, it can significantly improve the mission critical user service performance in our considered scenario. And also with the multi-UAV coordinated navigation can be enabled by multi-agent reinforcement learning algorithm without the centralized interaction by introducing the federated aggregation idea. So the reinforcement learning model generality is verified by quick adapting to user movements, and also the reward function design plays a very crucial role in the convergence status. So our future work is we would like to extend our current 2-dimension location navigation to 3-dimension location navigation, because now we only have X and Y axis. We would like to introduce the more axis like the height and also the how we rotate the drone and how we change the antenna tilt, etc. And also we would like to consider more requirement-based reward function design, and also we would like to validate our proposed algorithm in other application domain to see how it works in other environment. Yes. So thanks a lot.
Thank you, Hongyi.
Yep. Any questions? Yep.
And I think that from a talk on ecosystem engagement models, we all realized that this was the transition into the AI engineering theme. So thanks a lot, Hongyi.
Yep,
Do we
thank you.
have questions in the room or online? Do I see any waving hands? Yes, I do. Fredrik.
Hi, very nice talk, thank you. I have a question about stability of the control system. How do you ensure that you don't get, I mean, the rewards signals back to the system can make it unstable in the movement of the UAVs?
Yeah, I didn't find this kind of situation in our simulation because here our reward is very straightforward. We control the ratio of different kind of the metrics. Like we put very importance in the drop rate because we want everyone get connected. And then we have the 5 percentile throughput. So most of the people can have a kind of connection to the base station. Yes. But I mean, we are trying to introduce some of the like the penalties. Like if the drone is always focused on part of the person but ignore the others, and also we also observe that when we are trying to introduce a collaboration with each drone, it may have some of the interference with the others. So this is also something we are trying to explore and solve. Yes, yes, especially when we are introducing more drone in this scenario. Yeah.
Thank you.
Anyone else? The room seems happy. Okay, thank you very
Okay.
much, Hongyi.
Thank you very much.